Edexcel Pure Core, Hyperbolic Functions 2, Inverse Hyperbolic Functions, differentiating inverse hyperbolic functions. We're going to look at differentiating the inverse function sine minus 1x. Just to remind you that that is exactly the same notation as r sine x. So both notations are valid, and in your formula book they will use r sine x. So if we want to differentiate sine minus 1x, we can write it as y equals sine minus 1x. So we've defined y nice and clearly, and then we can rewrite this as sine y is the same as x. If we differentiate both sides with respect to x, so we're going to do this implicitly now. So sine y differentiated with respect to x becomes cosh y dy by dx. Differentiate x with respect to x is 1, and we can get dy by dx is 1 over cosh y. Now if we use the identity that cosh squared minus sine squared is 1, we can rewrite this as dy by dx is 1 over 2 possible square roots of 1 plus sine squared y. That's actually using the identity cosh squared minus sine squared is 1. But what do we know about the gradient of r sine x? We know the gradient of r sine x is definitely greater than 0. We saw that on an earlier video. So if the gradient is positive, then this gradient can be written as 1 over the positive square root of 1 plus, and if we look for sine y, we can find sine y here, and if we use that definition of sine y, this becomes x squared, and that is the derivative of the inverse function. So that is the gradient of the inverse hyperbolic function. So the key step here is to define y, but then go from the inverse hyperbolic function to the hyperbolic function sine y. Then we've differentiated implicitly, nice and carefully, and then we've used the identity to replace cosh y with plus or minus the square root of 1 plus sine squared y. The gradient of this inverse function is definitely positive, which gives us this nice derivative of r sine y. So an alternative method is to write the inverse hyperbolic function in its logarithmic form, and you can have a go at differentiating this logarithmic form either using the chain rule, or you will find it in many textbooks, but you should be able to differentiate this and show that you get exactly the same answer of 1 over the square root of 1 plus x squared. So just running through the process for differentiating the inverse of cosh, don't forget that can be written as r cosh x, and that's what we'd be using in a formula book. Write it as y is the inverse of x, and that gives us x is cosh y. Differentiate implicitly again, and then rearrange for dy by dx. We need an identity for sine y, and again we can use cosh squared minus sine squared is 1. So sine y is plus or minus the square root of cosh squared y minus 1, but we know if we think back to the inverse cosh graph, we know that the gradient must be greater than 0, and therefore we don't need this negative result for the gradient, and there is the gradient of the inverse of cosh of x. So there are two standard results. You will find both of these in a formula book, and more interestingly, in the future videos we're going to be looking at how we can use these interesting results to start to think about integrating things like 1 over the square root of 1 plus x squared dx, and integrating 1 over the square root of x squared minus 1 dx, which are functions which you haven't as yet been able to integrate. So just a little example here. We want to differentiate xi minus 1 of 4x. So if we let y equal xi minus 1 4x, and I can go straight to dy by dx. Just be careful here though, because we've got a 4x instead of x. So quoting the result, we're going to get 1 over the square root of 1 plus the bracket squared. But because it's a 4x and not an x, when we differentiate it, there will be a chain rule, and the 4x will chuck out its own derivative, which is 4. So this derivative could be written as 4 over the square root of 1 plus 16x squared. So just be careful when you're differentiating things like this, that because it's 4x, you need to watch out for the chain rule. So in the next video, we're going to be looking at integration using inverse hyperbolic functions.